Good morning, dear students. Welcome to another session of microwave and antenna. So, in previous discussions, we saw how do we obtain the radiation pattern for the linear array of n isotropic point sources for given conditions. Then we saw how we can obtain the half power beam width and beam width between first null for those radiation patterns identified. So next, we continue our discussion with the next part, in which we'll be discussing regarding the electric dipole and the thin linear antennas. So in this part, we'll be having a discussion mainly on analysis pertaining to the field parameters, that is magnetic and electric field pertaining to the dipoles and the thin linear antennas. And we'll have a discussion pertaining to the radiation resistance of the short electric dipole, and in which we have derivation related to that aspect. So what is basically a short, say a dipole? So when we consider a dipole, it is nothing but a combination of two charges which are opposite to each other. So and they are separated by some small distance between them. So this arrangement is called as a dipole. Therefore, such kind of arrangement is termed as a dipole. So in this, we can observe that we are having two charges, one is plus q and one is minus q. They are opposite to each other and they are separated by a distance L between them. So this arrangement is called as a dipole. Now, based on the distance between them, we can have that is distance between these two charges, and based on the operating wavelength, we can have some classification with respect to the dipoles. So, what are those classifications? We can have a classification as the dipole can be classified as a short electric dipole, or sometimes it is termed as Hertzian dipole. So when do we call this case? When we have the condition L is less than lambda by 10. If this condition is satisfied, then we classify the dipole as short dipole. If the length of this dipole is less than lambda by 10, then we classify the dipole as a short dipole. If this condition fails, then we do not classify it as a short dipole. So next, what we can have is we can have quarter wave dipole, half wave dipole. So all these specifications can come in. It is all based on the distance between these dipole. So if the length, that is the distance between the dipole, or the length of the dipole is lambda by 4, we can specify it as a quarter wave dipole. If it is equal to lambda by 2, we can specify it as a half wave dipole, and so on. Then we can have another classification as long wire dipole. If the length is greater than lambda by 2, then we classify the dipole as long wire dipole. Then apart from that, even we have another specification for thin linear antennas. So what happens to this one is, whenever you consider a wired structure, it will be having length, it will be having length, and it will be having a associated diameter, if this diameter is very small, if the diameter is very small, that is, if diameter of that wire is less than lambda by 100, then we classify that as thin linear antenna. We classify it as thin linear antenna. So this is what they have specified. So this is a dipole. There are two charges which are spaced by a distance L. And if the diameter of this wire, what we are considering, if it is less than lambda by 100, then we classify it as a thin linear antenna. And since we are specifying it as a dipole, it will be called a short dipole if it satisfies certain conditions. That is, its length should be, don't consider this parameter, its length should be less than lambda by 10. If this condition is satisfied, then it is a short dipole, or else it will be a it will be a non-short dipole. So these are the specifications pertaining to the dipoles. The same thing is specified over here. So here we it is like we are imagining two end plates which can be charged. So in order in to call an antenna structure, right, what we have is we have two wires which are placed in this form. Two wires which are placed in this form, and a source is applied to this antenna. And in previous sessions we had seen that how this structure can be called as an antenna. It has to radiate. It has to radiate. So if it is in the microwave range, what happens is during say one of the positive half cycle, say plus charge will be here and minus will be here, because all the electrons will be flowing and getting accumulated at one point. At the other point it will be all the other charges. So because of which what happens is you will be having positive and negative, and during the next half cycle what happens is these two cross each other and they get detached from the antenna. So this we had discussed in one of the sessions previously at the starting. So due to which what happens is you will be observing the radiations which will be emitted towards the transmitter. So therefore, this arrangement will be classified as an antenna. And why do we call it as a dipole antenna? It is based on we will be having two opposite charges, plus q and minus q, separated by a distance L between them. So such arrangement, we call it as a dipole antenna or Hertzian antenna, depending on the length. Now, this is the antenna representation for short dipole. Its equivalent, we can represent it as a wired structure. So wherein this is a wired kind of structure, wherein there are plus q and minus q charges and current is flowing through that, and the length of this antenna is L. And to be called as short dipole, again I specify the length should be less than lambda by 10, where lambda is what? The operating wavelength of the antenna. Lambda is the operating wavelength of the antenna. So this is the short dipole specification. So next point what we have to discuss is what are the fields which are pertaining to short dipole. So in order to discuss this, we will have a look over here. So fields of short dipole. So before going into this discussion, just a slight recap of few of the parameters. So whenever we consider an antenna element, so we have a condition which is given by r equal to 2 times L square by lambda. Now if I have if I satisfy the condition r greater equal to 2 times L square by lambda, if this condition is satisfied, right, then we specify that the observation is done in the far field. This r is nothing but the distance of the observation point with respect to the antenna. It is with respect to the antenna. So here what we have, so at a distance r, when we are considering, so this is a distance r, if this distance r, that is this observation point, satisfies the condition that it is greater than or equal to 2 times L square by lambda, then we specify that the observation is in the far field, or it is also termed as the Fraunhofer region. If this condition is not satisfying, if r is less than 2 times L square by lambda, then what happens is the observation point will be falling within this range. So this range will be specified as, say suppose it is somewhere here. So then what is happening? It is not satisfying this condition. So therefore what happens is we specify that the observation point is in the near field or the Fresnel region. Now we have a boundary condition associated with this. That is, If r is equal to 2 times L square by lambda, that is the observation point what you're considering, exactly it is in between these two. This is actually called the Fresnel-Fraunhofer zone, that is near field and far field zone. It is in combination. So it is like the critical boundary what it is serving. So any observation point beyond this will be in the far field region. Any observation point below this will be in the near field region. So why we are discussing this part is because we come across few of the concepts, that is when we are identifying the field parameters, that is the electric field and the magnetic field. So we need to identify these fields. So when we consider the observation point, based on that, I have near field and far field components. Near field and far field components. So if the observation is in the near field and we obtain the parameters for E and H, so these will be reflecting the near field parameters. But if the observation point is somewhere at a distant point, which is satisfying the condition that R is greater than 2 times L square by lambda. So if it is somewhere here and we obtain E and H for at this point, then we get to know that these are actually present in the far field region. So therefore we need to just have a recap of this part. So this is what we discussed previously. That is, this is how the dipole will be. It will be having two thin wires which are placed in this form, and there will be a source which will be applied to this antenna. And based on that source, right, we'll be having either a plus charge here or minus charge here, or it might be minus here and plus here, depending on whether it is positive half cycle or negative half cycle of the supply what you are giving over here. So due to which you have the radiation, therefore you have this antenna which is present. So this is nothing but transmission line which you are observing over here. Its equivalent is given over here. So this is the diagrammatic representation of the short dipole. Now remember, we are calling it as short dipole. So in this consideration, we have L is less than lambda by 10. So which basically implies what? L is very much less than lambda. So this is the condition, that the length of this dipole is very much lesser than the operating wavelength. So that is a consideration what we are looking out for. So now how do I obtain the fields for this dipole what we are discussing? So now in order to obtain the field representations, right, what we do is we consider its equivalent representation. So this is the dipole, short dipole, which is placed along the z-axis, and it is placed in such a way that z equal to 0, that is the origin point, forms the midway of this dipole. So if I measure the distance from this to this, it will be half of the length, that is it will be L by 2, and this one also will be L by 2. So this origin will be the reference point for us. So we are here, the arrangement is the dipole is placed along the z-axis such that the origin forms the midway of this dipole. And since we need to obtain the field components, right, we can obtain one of the field components, since what logic we have is we know that E cross H will give you the value of intrinsic impedance. And if I consider it to be say a free space, that is it will be equal to what? It will be equal to 377 ohm, or it is 120 pi ohm. So that is cross product of E and sorry, not cross product. It is the division of both. Sorry, it is E by H is equal to eta. That is the characteristic impedance. And if it is free space, right, it is equal to 377 ohm, which is also sometimes we specify it as 120 pi ohm. So here, if I identify one of the parameters, I can identify the other parameter. So using this equation, we can identify it. So therefore, they have just represented the electric field over here. So now what we are considering is from the origin. So if I assume that this antenna is placed in this form, I refer to the spherical coordinate system in which the coordinates are r, theta, and phi. So what we do is from this origin point at a distance r, that is with respect to point P, which is having azimuth angle of phi and elevation angle of theta. So therefore the coordinate of this one is what? In general, it is r, theta, phi. So at this point, I need to observe the field values. So here what we have, so at this point, I can have three components for the electric field. One is the radial component, which is identified by ER. Another one is the phi component, which is identified by E phi. Another one is the theta component, which is identified by E theta. So E phi is with respect to this phi direction, E theta is with respect to this theta direction, and ER is with respect to the radial direction. So these are the three components what we need to identify. So this is the geometrical representation of the dipole placed in the spherical coordinate system. Now here, so this point when I consider, so how do I geometrically represent it now? So we have a dipole which is of length L, and this is the origin point. So from origin point to the point of observation P, what is the distance? Distance is r. The distance from this origin point of the dipole, that is midway of the dipole, to the observation point is P. So now when we consider the two end this thing, right? So here I might be having plus q, here I might be having minus q. So based on this, what we have is with respect to one end of the dipole, the distance between this end of the dipole and the observation point is considered as S1, and distance between one and other end of the dipole and the observation point is considered as S2. So now when we want to make the observation, right, what we do is, so here another point is elevation angle. So if you just observe the elevation angle, what is the elevation angle with respect to this? It is equal to theta. So that is what is represented over here. So now when we want to obtain the field at this point, right, P, what we do is no need to consider the entire length of the dipole. What we do is we first identify what is the field due to a small element of the dipole, and then we take the summation of all those. So we can divide this dipole into small elements. So each element will be adding its field values at observation point. So what we do is we consider a small elemental point, say dz, of length dz, and what is the field due to this elemental point at the observation point. So field due to elemental this thing when it is obtained, so that you integrate it with respect to dz, you will be getting with respect to overall field which is being introduced because of the dipole. So here what we are assuming a small elemental length of the dipole which is of the length dz, and the distance between this elemental length and the observation point is considered as s. So now what is the other thing? So when we move this point at a far off distance, so what happens is these lines what we are observing, S1, R and S2, will almost be equal to parallel to each other, So that is the assumption what we make over here. So based on that assumption, since we are considering R is much greater than L, that is this length of the dipole and this distance, that is the point of observation, distance of the point of observation, when we consider, it will be very much greater than the length, because of which what happens is we can consider that these lines are parallel to each other. So when we are observing at a from a far off distance point, so due to this, what happens is, if I consider the field from this point, if this is the reference point, then what happens is the field due to this point is leading as compared to field due to the midway, and field due to S2, field due to this point is actually lagging by L by 2. Now, if I have to identify what is the length of S1 with respect to the observation point, it will be given with respect to R and the length of the dipole, the length of the dipole. So how do you obtain this? It is based on your Pythagoras, your right angle triangle, this thing, wherein you try to identify cos theta is equal to opposite upon adjacent. Cos theta is equal to opposite upon adjacent. Okay. So based on that, you are trying to obtain the equation. So here, what is S1 equal to? S1 is, so if you just observe from here to here, say if this is the observation point, from here to here, the distance is R, but S1 is shorter by this much. It is shorter by this much. Therefore, S1 is actually equal to R minus L by 2 cos theta. And if you continue this line, so this distance is actually equal to R. So therefore, S2, that is from this point to this point, S2 is actually equal to what? R plus L by 2 cos theta. So these are just a few things to note down before we start with knowing what is the field components. What are the field components? So these are the aspects or the parameters based on which we need to go ahead with identifying the relations of the electric and the magnetic field. So if we start off our discussion, actually there are few parameters. So we have a component which is called as A, which we specify as a retarded vector potential or vector retarded potential. We have a parameter which is termed as V, which we call it as a scalar retarded potential. Then after that, we look into the electric and magnetic field representations using A and V, that is vector and scalar retarded potentials respectively. So from that, we obtain the different components. So this is what we have to look ahead. So as we considered this dipole, right, previously, we have considered this dipole. So if we assume that there is a current flowing through this dipole, if there is a current flowing through this dipole, which is given by I is equal to I naught into e raised to j omega t, where I naught is the peak value of the current. Now, when you consider that at a distance point r, when you consider at a distance point r, what happens is the disturbance which is created, that is nothing but the radiation. So for the charge will be first plus q here and minus q here. Next, during the next cycle, what happens is it will change. That is next positive cycle. These two will change its value, due to which what we have is we have radiation involved with this. So due to that, what happens is the effect of this current is not immediately observed. Say a current I is flowing over here at a distance r, it is not observed immediately, but it is observed after some retardation. So how is that retardation obtained? That retardation is obtained based on the speed with which the wave travels and the distance between the antenna and the observation point. So therefore, what we refer is this is the current which is flowing through the dipole. But what about the retarded current? We need to consider the retarded current to make this analysis. So therefore, we have the retarded potential, retarded current, which is represented by I within the brackets. So in this case, what changes will be there? It will be I naught into e raised to j omega t minus r by c. So this is nothing but the retardation factor which we are including. So where r is what? R is the distance between the observation point and the antenna, and c is the speed with which the wave travels. So therefore, the extra timing which is required, say if I just specify it as t naught, it will be r by c, distance upon the speed with which it is traveling. So this is the parameter what we are having. So therefore, we consider it as t minus t naught. That is e raised to j omega. The t factor is replaced with t minus t naught, where t naught is r by c. So this is the retarded current. Now, this retarded current has to be utilized henceforth in order to make the analysis of the field. So, the first component which we have is retarded vector potential. So, this is a this is a potential retarded potential, but it is a vector quantity. But it is a vector quantity which is having a direction. So therefore, we term it as vector retarded potential, which is given by this equation, which is mu naught divided by 4 pi integration minus L by 2 to L by 2, because the integration falls only within the length of this dipole, which is placed along the z axis. So here we have, so if we consider this way, we have plus L by 2, and this side the value of Z will be minus L by 2. So therefore we have it as integration of this, that is retarded current divided by S. So which is given by dz. So where did this come from? This is coming from the small elemental length what we are considering over the dipole. So we are trying to estimate what is the vector retarded potential due to this small elemental length, which is having a distance of s. So it is all because of that. This s is coming from there. So now I is nothing but I naught into e raised to j omega t minus. Now what happens is the r value what you're considering is nothing but it will be equal to s over here. So in this case, it was with respect to the reference point, that is the midway. Now since we are considering small elemental length, right, of dz, so the distance parameter what is there, it is s. Therefore this gets replaced with s by c. So that is what we are having. So this is the vector retarded potential, and where I is the I which is present in the bracket is nothing but the retarded current, which is due to the small elemental length of the dipole. So if you integrate this, you will be getting the overall retarded potential. So therefore, when you simplify the equation, you will be ending up with a vector retarded potential in z direction, which is given by this equation, which is mu naught L into I naught e raised to j omega t minus r by c divided by 4 pi r. So this is the equation for vector retarded potential. Now similarly for scalar retarded potential, which is identified by capital V, it is given by the integration of 1 by 4 pi epsilon naught integration over V. This is the charge density. This is the retarded charge density. This is the retarded charge density over the elemental surface what we are considering, divided by S. So where we have the retarded charge density, which is given by rho naught e raised to j omega t minus s by c. When we simplify this equation, we get it in terms of charge. Since in dipole, as we specified, we have a plus q charge over here and minus q charge over here. Therefore, in general, the charges what we are considering is of q coulombs. So based on that, we end up with this equation, which is actually q1 and q2, what we specify. So this is actually q1 and this is actually q2, because we have plus q and minus q. That is where the this is the potential at this end. That is because of this distance s1, because of this distance s2, we have these potentials. So therefore, when we simplify this equation, right, we end up with this. When we simplify this integration, we end up with 1 by 4 pi epsilon naught integration retarded charge q1 divided by s1 minus retarded charge q2 minus s2. So this one is what? So this, that is, from this point the distance is s1 and from this point the distance is s2. So we are considering at this point the potential which is introduced at the distance point. So where the retarded charge is given by integration of retarded current into dt, because if you remember we have dq by dt which is equal to current. This is in general equation. So therefore if you consider the retarded charge, right, it will be differentiation of the retarded charge with respect to time, which will be equal to the retarded current. So therefore what we have, we'll be having the overall dq which is equal to retarded current into dt. And when we take integration of this, what we have, we equate this one to the retarded charge which is equal to integration of retarded current into with respect to t. So this is what we are having. So therefore, when we simplify this parameter, right, what we have is we have it as retarded current divided by j omega. So the two equations, what we consider is retarded vector retarded potential and the scalar retarded potential. So we end up with these two parameters. We end up with these two parameters. This one still, when we further simplify it, what we have is, by substituting this in this equation, what we have is we obtain v in this form. And when we observe that S1 is R minus L by 2 cos theta and S2 is R plus L by 2 cos theta, we have the overall scalar retarded potential, which is given by I naught into L cos theta e raised to j omega t minus R by C divided by 4 pi epsilon naught into C, where C is the speed of light. So mu is the permeability and epsilon is the permittivity. So if it is mu naught, it is the free space permeability, and epsilon naught is the free space permittivity. So we obtain this as into 1 by r plus c divided by j omega divided by r square. So in some cases what they do is they replace beta with omega c. So to simplify the equation, they replace, if there is any term with omega c. In some books, you might observe that this is replaced by 1 by j beta, or sometimes even they use the term k. So these are just different notations which you will be having. So overall, we have two representation. This is the vector retarded potential. This is the scalar retarded potential. Now using these two equations, right, we need to obtain the field values. Now what is electric field given in terms of A and V? That is the vector retarded potential and scalar retarded potential. It is given by minus j omega A minus del V. And what is H given by? H is given by 1 by mu del cross A. So this is using these two equations, we need to identify the electric field components and the magnetic field components. So now since we can observe that A can be represented in r theta phi phi representations, since we have only AZ over here. So if I convert that using that AZ, I'll be able to obtain AR and A theta also. I'll be able to obtain AR and A theta, where AR is given by AZ into cos theta and A theta is given by minus AZ into sin theta. So referring to these equations, right, referring to these parameters, we end up with we end up with all these equations wherein we equate the r component, theta component, and phi component of right hand side and left hand side of this equation. We have this parameter. We equate right hand side and left hand side of this parameter. We have this equation. So wherein del phi is given by this equation. So when we substitute this over here and these two over here, we equate right hand side and left hand side for r, theta, and phi components. We end up with these equations. So now when we substitute ar and v, a phi and v, and a phi over here and v over here, we obtain these field components. We obtain these field components. So we have a radial component for electric field for the orientation what we have considered. We have E theta and E phi is 0. E phi is 0. So these are all are obtained after simplifying those equations. So next, remember that E and H are perpendicular to each other. So therefore, what happens is, if you have a component for ER, you cannot have HR component. And if you have component for E theta, you cannot have H theta component. So therefore, because of that, what happens is, you when you simplify the other equation also, you get to know that HR and H theta are equal to 0. HR and H theta are equal to 0. Either use that condition or you use this equation over here. You use this equation and simplify, or you refer to the cross product and try to obtain the result. That is, you obtain E cross H and try to see what is the result over there. So here we have E phi 0. And what about the H phi component? Since E phi is there, it makes a possibility that H phi might be present. So if in this case, we have H phi, which is given by this equation, So here, what do we have is these components, what they have specified. These components, what they have specified are actually near field components. These are near field components. Now, what about the far field components over here? What about the far field components? So these equations are actually relevant to near field components. So we observe that for near field, we have which all parameters? We have ER, E theta, and H phi components. But for remaining, we have E phi is 0, HR is 0, H theta is 0. So this is for this orientation what we are considering. That is this case. The dipole is placed along z axis and at a distance r from the origin. We are considering the observation point, and based on that we are making the observation. So based on this, what we have at that point, we have ER, E theta, and H phi components. So these are actually near field components. Now for far field, how do I obtain this representation? Now what is considered is, so if I obtain the field values, I got to know that ER, E theta, and H phi are present at this point. So this is near field. So if this observation point is moved further such that this R what you are considering, R satisfies 2 times greater than 2 L square divided by lambda. That is, R is greater than equal to 2 times L square by lambda. If this condition is satisfied, then the point P will be under the far field condition. So indirectly what you're doing is you are increasing this distance. So if you're increasing the distance, what happens is, based on these equations itself, based on these equations itself, I can obtain what is the far field component. So when distance increases, and we consider that this is in the far field, when this point is in the far field. So what happens is, here we can observe that we have components associated with 1 by r, 1 by r square, and 1 by r cube. So three parameters we can observe. So here you can see that you have 1 by r square, here you have 1 by r cube, here you have 1 by r, 1 by r square, 1 by r cube, so 1 by r square, and here 1 by r. So what we do is, so if I consider r is very much in the far field, then what we can do is we can consider the assumption that 1 by r square is very much smaller and 1 by r cube is also very much smaller. So therefore what we do is we equate these parameters to nearly zero, nearly zero. So if we equate these parameters to nearly equal to zero, what we have is, we can observe over here. So here 1 by r square is there, and here 1 by r cube is there. So this parameter will be nearly equal to 0, and this parameter will be nearly equal to 0. So therefore what happens is, in the far field, because of this assumption, we have radial component equated to 0. Now what about E theta? E theta, this component is equated to 0 and this component is equated to 0. So therefore you are left with only this parameter. So this will be the equation for E theta in the far field, and E phi will be 0. It is not present in the near field, therefore it will not be present even in the far field. Now what about H phi? So H phi, we can observe that here we have 1 by r square. So this one gets equated to 0. We are left only with this parameter. So therefore we have H phi in the far field, which is given by this part, only this parameter, and HR and H theta in the far field are 0. So therefore based on this, what you observe in the far field, you observe that in the far field you have only E theta and H phi component. You have only E theta and H phi component, whereas remaining all components, that is ER, then HR, H theta, and E phi, all these components are 0 in the far field. So in near field I have ER, E theta, H phi, but in far field I have only E theta and H phi components. So these are the fields which are associated with the short dipole. So these are the near field components. For far field, you have to equate 1 by r square and 1 by r cube to 0. You'll be getting the far field components. So this is all for today. Let us meet in the next session. Thank you. So anything from your end?